So first of all, you can see here the agenda. We are going to have a welcome and then a little presentation of very high level of the advanced production planning and scheduling system. That is what as a Better Factory partners we are going to develop during the project. Then we will have some presentations for each APPS package, and per each APPS package we will have examples taking from real use cases, so that we will give you some examples on how you could interface your technology and what you are going to propose with each package of the APPS system. As you can see, I wrote down the presenter. These people for sure are in the call, and then you could contact them and directly contact the organizer of this event in order to have more information. And at the end, we will have like 30 minutes for questions and answers. So if everything is clear, I think that we could start with the presentation of the APPS. First of all, what is APPS? Aims to provide a complete digital infrastructure needed by manufacturing SME. As you can see, this is an infrastructure mainly made by 4 blocks. These blocks are the cognitive HRI, the logistics automation and optimization, the resource optimization, and then production reconfiguration. During today's call, we will go in detail of this block to understand how it will be made and which main capabilities it can offer. This APPS is connecting to the production process of a company and also with RAMP, because in this project we are going to work with the RAMP IoT platform that is able to be connected directly to machine, to robots, to ERP, to sensor that you can have in your company or in general in a case. And this is the flow that we will follow. So you can see, as anticipated, that we have 4 main blocks. The first one that you will see will be the cognitive HRI. This module supports human-machine collaboration in order to combine the human flexibility with the repeatability of automated factory entities, such as cobots, such as all kind of devices that you can have in a company environment or directly on a worker. These cognitive HRI blocks as 3 main technologies involved, that are the fatigue monitoring system, the intervention manager, and the pose recognition and correction. After we will see the detail of these 3 technology. The second block is the logistics and automation. In these blocks, we are going to optimize all route, agents, material flow, resources that you can have in production. And we have a lot of technologies used in this block that are like real-time locating system, material flow, agent optimization, temporal heat maps, and logistics library. So all this technology will help a company to automate and optimize their main resource utilization. Then we have the resource optimization. This module is made in order to guarantee to companies the optimization of resources in terms of energy, resources, waste, and moreover, we are going to have also some data analytics tool in order to minimize consumption, in order to have real-time data visualization, time, effort, resource optimization. And in this block, We will have Grafana dashboard, that is something already present in the ramp, but we will offer to companies this tool. Then the business process optimization and the production optimization. In the end, we have the fourth block, that is the production reconfiguration. The production reconfiguration refers to the reconfiguration of the production line and to the tasks of the automated and human actors, like robots, workers, equipment in the production floor, in order to produce different variants, personalization of a product. And we have as technologies, manufacturing process management system and advanced plant model. So as you can see, we made a very quick going through the four main blocks of the PPS.
I'd like to guide you through the first block of the APPS we want to, or which will be part of the ramp or a better factory system. And our first block is about the cognitive human-robot interaction. And as Serena mentioned, it shall help to make the human robot collaboration more effective and less dangerous in respect to human errors. So what is the cognitive human-robot interaction? So actually, currently we are seeing a trend in production that human and robots work together, especially on complex tasks like assembly tasks or others. And currently these complex tasks are not replaced by robots. They are actually humans and robots working together on a collaborative basis. Can you go to the next slide, please? So what is our module? So our module supports the human-machine collaboration, and with the aim of increasing the flexibility and also the repeatability of task performed, and also the effectiveness of the work to be done. And the scenario, what we are currently offering, consists of actually three modules by themselves. So on the first module, the worker's exertion level is detected by a so-called fatigue monitoring system. In a second module, we have an ergonomic module for detection the worker's posture, and on the third module, both of these detection modules will be fusioned in order to get information or to reorganize the work, that the work is more effective. So can you go to the next slide, please? So how does it look like? So we have it in a first step, we have the worker in a collaboration with the machine, so actually a robot in this way. And the worker will be equipped with wearables, for example, a smartwatch, and also a camera will be attached, will be have a view on the worker itself. And the data will be transferred through a middleware. Can you, the next slide? Yes. Then the data will actually be transformed into a digital twin of the worker itself, and will have information about the physiological data, the ergonomic data, and also about the task and the environment. And then can you please go to the next? These information from the digital twin will be fusioned and go to the intervention manager. There in the intervention manager, the reasoning will give information about, will make suggestions and give in a later stage the information back to the worker. can do. And therefore, this information can be then either just displayed to the worker that he's, for example, has a high fatigue level and should make a pause, or the robot will adapt, for example, in a collaborative environment to the worker and give information will be attached will be, for example, lower the speed if the or will be higher the speed if it's in a good condition. So this is just an information about these. As I said, there are 3 modules. It's the fatigue monitoring system, which will use like static data, which come from a questionnaire, so that you can like get an individual information about the worker himself. And then there will be dynamical data from the wearable devices. These will be fusioned in the fatigue monitoring system, and we'll get an output about the worker's perceived exertion level. The next module will be the pose recognition and correction module. So the pose will be identified by a camera, in this case an RGB camera, and will be also this data will be also configured, will be also fusioned with configuration data, and then the pose will be recognized, and there will be about the given configurations, there will be made suggestions about the correct ergonomic pose of the worker, and there will be given some pose recommendation. And on the last stage, there will be both modules will be fusioned in the intervention manager, and this is more or less an automatic triggering of the best possible pose either, and also the best working speed, or in order to get the worker the most effective information about it. So on the next slide, there's an example of, for example, the pose correction. So you see the worker's pose is determined. You see it's the ergonomic pose is not good, and so the robot is adapting to it. The next slide. Oh, there was a video missing. That's it. I think you skipped one. Yeah. That's the example about the, no. Unfortunately, the video is not working.
No, the first video is not working, I think.
Yeah.
Yeah. There is a, no, let me see. Oh, no, yes.
Yes, yeah. Because it's a YouTube link.
Yeah, yes, okay.
It's a little bit longer. You can skip the first 1.5 minutes of the video. It's just a previous explanation.
Is it okay here?
1.5 minutes. You're still like, it's just the explanation of the task. Actually, it's just yeah, now it's good. So it's actually just an assembly task where still having problems. Okay, now it's good. Yeah. So you see now here's the wearable device where you can like choose the workers presettings, so which are connected to the questionnaire, which as a static data, and then on a dynamic data, the smartwatch gives information about the worker status and about the awareness of the worker, and the robot later on is actually adapting to the workers themselves. You see there are a lot of more options to be integrated. So and you can also work with light systems in order to make it more efficient. You are also able to integrate different software and hardware components, and they are, for example, for a wristband, you can have integrate, for example, the Empatica wristband or Huawei watch. Also, Polar body band can be integrated, and these will be integrated to the system to the Better Factory system.
The next presented block is called Logistics and Automation. It optimizes roads, agents, material flow in the production. The following listed technologies are involved: the real-time locating system, material flow, agent optimization, temporal heat maps, and person detection and tracking are new modules which will be implemented on RAM. The logistics library is an already existing and used library. The first, we will say some words about the logistic library. It is an open Internet of Things platform that exploits the IoT paradigm to enhance communication among the different elements of the shop floor in order to create a flexible and responsive logistic system, either on planning, in the simulation phase, same as executing, as can be seen in the picture. If you are interested in this platform, you can find more information about it using the link below. Here is a schematic of how the logistic library interacts with all the implemented equipment and devices of the factory, like sensors, AGVs, as well as the enterprise applications. Also, it interacts with virtual component simulation software, which is a digital twin of the whole logistics system. From the previous schematic, we can examine another functionality of this platform. We can separate it into phases. The planning phase, where the simulation can be used to design the layout, roads, and schedule routines of the floor plan, and the execution phase, where devices can be connected and any logistic operation can be steered. The platform enables, moreover, the continuous adaptation and reconfiguration of the logistic system with low effort and maximum efficiency. So the question is, why to use this platform? Material handling is a non-value adding activity. There is a big uncertainty regarding future demand requirements, also uncertainty in future product portfolio. Of course, in modern factory, there are automated logistic, but they have traditionally low adaptability. Also, integration cost due to software integration is always high, as well as system expansion, which is most of the times costly and times consuming. OPIL platform can adapt easily to new layouts because you can always design and redesign and optimize roads and speed with precision through the virtual component simulations. Also, you have high adaptation to changing volumes. For example, it's easy to include new AGVs, robots, and so on, or change the production planning and consider even automatic scheduling. Also, adaptation to new technologies is possible with a plug-and-play functionality to sensors and robot operating system based AGVs. So on the technical tools, there is a robotic operating system where it provides libraries specially developed for robot control, and it can communicate with the firmware Orion Contact browser. That is a data distributed service where every node of the logistic library can be read and write messages, and the tool is used by the nodes of the architecture to communicate. So both tools communicate with the software called Firos, which can establish communication between robots, AGVs, and main control of the logistic library. The architecture of the library consists from 3 layers. The lower layer is the Internet of Things nodes, that is a production floor, and the ones that perform logistic tasks. Then there is an upper layer, which is a software system layer, which is responsible for logistics functionality and simulation, and a middle layer, the cyber-physical system layer, which enables communication among different systems. So concerning functionality of the OPIL library, we can distinguish 2 main functions of it, steer and inform. At the right, you can see clearly what steering is about. Here are the modules that are responsible for the reading and communication of the sensor signals, like sensor agent node and the nodes responsible for AGVs and the robot to perform operations and follow planned tasks. The robot agent node, so-called run node, that is running on a local device. In parallel, there are 2 nodes exist in the digital twin as a robotic agent node and sensor agent node, and another module, the actuator, which is a combination of real sensor signals and simulation. On the left part, you can see the function modules that determine operations, plan and tasks for the floor plan, and ensure the smart behavior of the whole structure. These modules are the task planner, sensing and perception, and the human machine interaction modules, which are running on the OPIL library server. The next module, which will be included, is called agent optimization. It's a new module in the existing logistic library. The aim of the module is to determine the optimal number of agents for material transport. Under agent, we can imagine AGV, human, and so on. This module will require the following inputs: the distance matrix, which represents the distances between stations; flow rate matrix is which represents the material flow rate between the stations for all the agents; and finally the agent parameters like agent speed, time to load and unload the material, and so on. The inputs are planned to be entered manually using graphical user interface into the system, and also by preprocessing the data from material flow node. This node will generate inputs from databases or directly from existing modules of logistics library. The principle is shown in this picture. On the left side, you can see the existing nodes of the library. The material flow and the agent optimization will be included. The real-time locating system will log data into databases. Then the material flow will analyze these data and preprocess them into required format for agent optimization. And on the top of them, there is a human-machine interface layer, which will be extended. The next module is called Temporal heat maps. Temporal heat maps is a geographically representation of data that uses a system of color coding to represent different values. In the example, the AGVs have their road, let's be it horizontal in this way. Persons crossing this road can slow down or even stop the AGVs. Therefore, the shortest path is not always the fastest path. In the example, using the alternative road with full AGV speed, the transport can be shorter. The state of the traffic can differ in different time periods. In the example on the left, there are no obstacles, but during the lunchtime in the example on the right, you can see increased traffic. This can be used to replan the roads for AGVs. This module will use LiDARs to monitor the traffic and provide time-specific heat maps. During this project, 10 LiDARs can be installed for a period of 2 weeks for data collection. The requirements are wireless or local area network connection with internet access. The output will be a heat map with a resolution of 1 hour and 1 square meter. The last module is a person detecting and tracking. This module can be used to monitor the occupancy of the shop floor using stereo pair from a regular, shop floor using stereo pairs from regular 2D cameras. It is intended to be used in shared space between robots and humans, like it was in the case of heat map, and allows for dynamic replanning when people are detecting either at the global planning level or robotic local level. In the left picture, you can see examples of detection of workers and pose estimation using RGB cameras, and the output is on the right. It shows the occupancy grid map. So now we will proceed to examples of logistic library. 2 success stories were selected. The first one, an Italian company where the raw materials and half-finished products were carried in cases from station to station by the workers. The process was split into 2 separate floors, which means workers were spending a considerable amount of time waiting for the elevator. A digital twin was created to simulate current and future paths and also all functions of Jobot. The Jobot will pick up and deliver loads between workstation and use the elevator independently whenever needed. As a result, the time spent on manually moving materials by workers was reduced significantly from 20 to approximately 2%. The next use case is a shoe company manufacturer. By improving the indoor logistics, they wanted to reduce machine downtime and improve just-in-time delivery in the factory. The company also wanted to improve the safety of the workers during the mold change operation. Therefore, the solution was divided into parts. So the first one, design material handling solution, where the AGVs delivers the materials boxes to a set of gravity-based conveyors. OPIL library was used to integrate each task as a mission, giving coordinates for each task as the infrared sensor detects the box. And for the second part, a mold change structure was created to help the mold change operation, where the OPIL serves the operator with the sub orders of the day, identifying which part molds are needed. The results are increased productivity, reduced number of accidents, and 0 accidents occurrence during change. The last use case is for the agent optimization node. The data presented will be entered manually for this use case. First, we have to define the layout, so the scale and the station positions. For example, you can see in the picture in the right, the numbers representing the stations. For example, here we have the station number 1, which is defined with 5510 coordinate. Then we define the path between the stations. So for example, we want to transfer some material from station 1 to station 2 using this point. So 110 is defined as a point of the road. Then we define agent parameters. In this use case, we define 2 agents with the same parameters. They differ only with the capacity to show that by increasing the capacity, the number of agents should decrease. So this is for the second agent. Then we can define the flow rate for each agent, but in this use case, we used the same flow rates to compare the results. So these are the flow rates. So the calculations are the following. So the distance matrix, the flow rate matrix is, they are the inputs for this module. And finally, the results. So we are interested in the number of optimal number or minimal number of agents. So in the first case for the agent 171, and for the second one, the number has, of course, reduced. So thank you for the attention, and I pass the word to the next presenter.
Thank you. So resource optimization and by top data science relating to better factory and this solution and technology offering that we are building up together with the consortium. So our role in the project is focus on resource optimization and to provide that utilizing latest artificial intelligence technologies. And we have implemented this technology with great success to pulp and paper industry, but the same approach and technology capabilities can be applied to different type of production processes and different industries. The very powerful element in this technology is deep learning, and we have long experience and a lot of different type of use cases in utilizing machine learning, deep learning technologies and algorithms, and they are in the focus on this development as well. In this picture and slide, I'm describing the overall logic and how this can how this approach can be applied to different production processes. So on the right hand side graphics, there is a simplistic graphics on the logic that this technology solution has. Of course, this is implemented in this RAMP IoT platform and platform ecosystem environment. But to simplify the overall logic, it is based on well-functioning interfaces, which on one hand is used to set certain constraints to production that can be relating to time or any like a production fact that needs to be taken into account when we are optimizing a production process. Then always in these type of processes, there are such parameters that you can control. So you can add warm temperature, you can decrease pressure, you can add chemicals or such likes. And then on the right hand side, this optimization is providing the optimal production outcome through this AI-based optimization, and also as an input to the process, what parameters should be used in order to achieve this optimal performance the process. This can be implemented to a simple process, which is only like one stage. The input going in, it is controlled, and then there is output, and then the process continues to work. Or it can be divided to different stages, like in a complex, more complex scenario. So how this is then implemented is that the process itself and its stages need to be defined. What is the thing that we want to optimize? So what are the criteria that this optimization is done? So in those in use case example that I'm going to share with you, I will explain one example of this type of optimization objective. What are the input parameters? How do we integrate? So utilizing this ramp, what is it in practice to create the data pipelines? What historical data is available? So that is of course utilized then when the deep learning is implemented. So learn from existing data. And depending on the process, there might be already existing like generic models that could be utilized in this optimization. Then kind of a fine-tuning this optimization utilizing artificial intelligence, and then testing the model and verifying that the performance is improved as expected through this approach. So this is what is provided through this ramp architecture, overall architecture, and specific to this resource optimization, chemical optimization, if you will. Then just summarizing what is the result of this optimization is optimal future process performance and the parameters that needs to be used and set in order to achieve this optimal performance. Real example of utilizing this technology approach is one that we have implemented together with a global leader in pulp and paper industry. So in our case, the product name is AI. So AI for your advantage, like abbreviation from that. And here we designed and implemented a very intuitive and easy to use user interface, so end user application that is seen on the right hand side. So this parameter view is showing the historical performance of this process, and there are like measuring points being those white dots. And then it's showing how the process and production will perform going forward. So within the next hours or days, depending how this is modeled. These stages on the lower hand side, or on the lower side of the UI, is then the simplistic UI components that you can use to modify the parameters of the process. So instantly when you move that parameter component in the UI, you can see instantly how the process is going to change. So how it will behave, how it will be behaving based on this real-time modification to the process performance or process control. So this is the overall logic that this solution has, and what then it enables. So on the right hand side, you can see that there are production personnel that are using real-time controls to modify the pulp production, and it is super intuitive and the outcome is very accuracy, and not just this functionality, but the real benefit, for example, comes from minimizing the use of chemicals and other raw materials, whatever they may be. The end users are able to simulate that how the production will behave when I use these type of parameters instead of those that has been used traditionally. And also this kind of advisory tool is making the work more transparent. So it is more easy to really communicate how the production process will behave, and based on what facts and data and controls. Just wrapping it up, what are the benefits coming from this type of technology? And although these are like proven from this pulp and paper industry use case and our success there, these are really applicable to many other industries as well. So it's a lower risk and higher predictability of the process, and also having this scenario analysis to really understand that if these type of modifications are done, what are the benefits and what are the risks that are coming through these type of changes in the process. Cost savings through minimized use of resources, and I was commenting that what are the objective for this type of process optimization. In case of pulp, for example, it is the brightness of this pulp, it is the strength of the pulp, and that needs to be exactly something that is sold to the end customers, not better, not worse, so that they can maximize the profit out of the production. And then also improve decision making based on facts and big transparency in communicating how the production is then run as an organization, also towards management and to the operative personnel. So this was my presentation relating to resource optimization. Thank you.
Thank you very much. Thank you very much, Kai.